Offshore wind development requires massive upfront capital. Projects live or die by the accuracy of their long-term energy projections. Look at this coastal region near the Gulf of Khambhat in western India. Imagine placing a 600-megawatt test site here, consisting of exactly 100 Siemens SWT 6.0154 turbines. When calculating the annual power generation for this array, engineers encountered two different projections. One model output 1.80 terawatt-hours. Another calculated 2.06. This 255 gigawatt-hour gap is a direct result of different methodologies for constructing historical wind data. Securing the billions of dollars required for project financing means proving interannual wind reliability over a 20 to 30-year lifespan. Investors require hard proof that the wind will consistently blow decades from now. Relying on standard historical data without applying localized corrections leads to artificially low projections. This specific math error can condemn viable wind projects before a single foundation is laid. To gather decades of historical wind data, you might assume developers just build a tall weather tower in the ocean. But installing offshore meteorological masts in deep water is technically complex and prohibitively expensive. The industry standard solution uses global reanalysis datasets, like ERA-5 or MERA-2. These are massive atmospheric models, simulating historical weather across the entire planet. ERA-5 models operate on broad grids, dividing the surface into 31 kilometer squares. When a single square covers a coastal gulf, the mathematics smooths out local microclimates. High-speed wind funnels created by topography get averaged down to a lower median speed. Because of this spatial averaging, global reanalysis models consistently underestimate true coastal wind speeds. Taking raw global datasets at face value for a micro-level wind resource assessment introduces a systemic, pessimistic bias into all capacity calculations. The solution to the resolution gap is targeted calibration. By capturing a high-fidelity local sample, engineers adjust the global model. Off the coast of Gujarat, researchers deployed a WindCube V2 LIDAR station. Anchored 23 kilometers offshore, this floating buoy fired a vertical laser pulse into the boundary layer, recording precise wind data in 10-minute intervals for 8 months. The first aerodynamic property this LIDAR captures is wind shear, which measures exactly how wind speed increases as elevation rises. The physics of the specific site dictate this flow. The marine environment has extremely low surface friction, classifying the area as roughness class 0. This table and graph show how that incredibly smooth surface results in a low power law exponent of 0.087, generating a highly efficient wind profile. Isolating the 100-meter turbine hub height reveals an actual mean wind speed of 7.41 meters per second. That measured velocity aligns perfectly with operational curves designed for large rotor IEC Class 3 and 2 turbines. The LIDAR confirms an undeniable physical reality. The actual wind passing through the turbine's swept area is significantly stronger than the global models suggest. With the baseline established, the next task is cross-referencing 8 months of LIDAR data against 4 competing long-term reanalysis models. This scatterplot aligns our contenders: EMD-ERA, CFSR2, MERA-2, and ERA-5, measuring their error rates against the physical LIDAR baseline of 7.41 meters per second. Due to the resolution gap, every single dataset falls short, clustering in the 6.1 to 6.8 range. While CFSR2 and MERA-2 are closer in raw average speed, prioritizing raw averages isn't enough. We have to optimize for statistical predictability over time. Isolating the ERA-5 dataset reveals it has the lowest root mean square error, deviating by only 0.68 meters per second. ERA-5 also maintains the highest correlation coefficient of 0.9329, meaning its simulated trends most accurately mirror real-world aerodynamics. Because its errors are mathematically consistent, ERA-5 is the most reliable dataset to historically calibrate. Engineers can now fuse the localized spatial accuracy of the LIDAR station with the 40-year continuity of ERA-5, using a linear regression fit. This bias correction formula recalculates the historical ERA-5 simulation into a true LIDAR equivalent dataset. Applying the regression bumps the long-term ERA-5 mean wind speed up from 6.77 to 7.28 meters per second, a seemingly modest velocity adjustment of 7.53%. Why go through this complex meteorological exercise for a mere 7.5% linear increase? The answer dictates the entire economics of the industry. Wind power density is governed by the cube of the wind velocity. Feeding that 7.5% velocity increase through the cubic equation yields a massive 14.08% spike in actual power output. In wind physics, marginal data underestimations cascade exponentially into massive financial miscalculations. By taking this newly corrected 40-year historical dataset, we can accurately evaluate the conceptual 600-megawatt wind farm off the coast of Gujarat. This energy rose diagram for the 100-meter hub height confirms geographic viability, proving the wind's directional energy is concentrated intensely from the south-southwest. Recall the original projection based entirely on raw, uncorrected global data. That model predicted a capacity factor of 34.42% and an annual generation of 1,809 gigawatt-hours. Presenting this artificially depressed capacity factor could cause investors to abandon a viable project. But with the final, mathematically verified LIDAR regression projections, the capacity factor climbs to 39.27%, increasing generation to 2,064 gigawatt-hours, recovering the missing 14%. Global reanalysis datasets are indispensable for their temporal length, but they remain blind to the localized aerodynamic mechanics of coastal shores. High-fidelity local calibration provides the statistical foundation needed to prove that offshore wind sites are significantly more productive than global models suggest.